Last time we talked about the integration of f of dx when f of x is defined as n equals 0 to infinity cn times x minus a to the n power. And this series converges. So integration of that series can be written as term by term integration. We will do the examples related to this. So the first one is f of x is tangent inverse of x. Then its derivative f prime of x is 1 over 1 plus x squared. And so by the fundamental theorem of calculus, its antiderivative will become tangent inverse. That means tangent inverse can be written as integration of f prime of x dx. So that is integration 1 over 1 plus x squared dx. So that equals integration 1 over 1 minus x squared dx. So we can expand that as a power series, and then that is integration summation n equals 0 to infinity negative x squared to the n power dx. This can be rewritten as integration summation n equals 0 to infinity negative 1 to the n power x to the 2n power dx. Since this is a convergent series, we can exchange the sum and the integration. So this can be written as summation n equals 0 to infinity integration minus 1 to the n power x to the 2n power dx. So that is summation n equals 0 to infinity negative 1 to the n power times x to the 2n plus 1 over 2n plus 1 plus c. Now we have to determine c. So what we know about the tangent is the graph of tangent look like this. So this is minus pi over 2. This is pi over 2. This is graph of tangent. Y equals tangent of x. So we know that tangent of 0 equals 0. Therefore, tangent inverse of 0 equals 0. So we can apply that to here. Then we know that 0 is tangent inverse of 0 from here. And then we think about this part. So that becomes summation n equals 0 to infinity, negative 1 to the n power times 0 to the 2n plus 1 over 2n plus 1 plus c. So that means this part will vanish. So c equals 0. So therefore, we go back to here and we conclude that tangent inverse of x equals summation n equals 0 to infinity, negative 1 to the n power, x to the 2n plus 1 power over 2n plus 1. So just we ignore this part. So do you have any question? Because all of you came a little bit late, and so I start earlier than you came. So if there is any ambiguity, then you can ask me questions. Otherwise, I will keep going. At the beginning, what I was saying was we want to think about the power series expansion for tangent inverse. And what we realized is when we differentiate, we get this one. And we know we can expand this as power series. So by the fundamental theorem of calculus, if we integrate, then we can get this function. So that's what is going on here. And then the remaining part is the same as before. So we use the power series expansion for this one. After we modify a little bit to use 1 over 1 minus x equals summation n equals 0 to infinity x to the n power. So let's move on.
Did you find what C was? Or did you just leave it as
Yeah,
C?
so I did. Well, plus C, right? So what I did was tangent inverse of 0 equals 0, right? And that equals this part, right? And if I plug that 0 into here, then this part will vanish. And so C is the same as tangent inverse of 0, right? What I was saying was tangent inverse of 0 is 0, and so C equals 0. Do you have any other question?
No, thank you.
Okay. The next one is g of x equals tangent inverse of x over 5 . G of x is tangent inverse of x over 5. So we can say that g of x is a f of x over 5, right? And so tangent inverse of f of x over 5. So we already did expansion. So that equals summation n equals 0 to infinity, -1 to the n power times x over 5 to the 2n plus 1 over 2n plus 1. So this one is a summation n equals 0 to infinity, -1 to the n power times x to the 2n plus 1 power over 5 to the 2n plus 1 power times the denominator. This is just the numerator, so we just multiply like this, and denominator is 1 over, can be written as 1 over 2n plus 1, right? So actually, I think probably it was better to combine all those things. And so n equals 0 to infinity, -1 to the n power, x over 5 to the 2n plus 1 times 1 over 2n plus 1. So this one had to be skipped. So just a numerator times 1 over denominator. So by looking at this, we know that the series converges if absolute value of x over 5 is less than 1. So series converges when x is less than 5. So the radius of convergence is 5. So we are finishing 11.8. 11.9 is about the representation of functions as power series. No, it's not Taylor series actually. 11.10. We are finishing 11.9, and 11.10 is Taylor and Maclaurin series. So important formula you have to remember is about the Taylor series of the function at A. So f of x, the Taylor series expansion is n equals 0 to infinity, nth derivative of f at a over n factorial times x minus a to the n power. If we expand that out, then we get f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial x minus a cubed and so on. So we are using the nth derivative to expand the given function with power series. And that is called Taylor series when a is not 0. In the previous section, we learned about the power series representation of f at a. And that was written as f of x equals c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on. And so x, and we thought about the radius of convergence when absolute value of x minus a is less than r. So here, what we can say is f of a equals, if you plug a in here, then all terms will vanish, and we have c0. So we have this term, and what we are doing is we want to relate this power series representation with the nth derivative, and we are just proving that this is the correct formula when the function has a power series representation. So C0 was this one, and then we want to think about f prime of a. So f prime of x equals, the first one will vanish, and the second one is C1, plus the third one is 2C2 x minus a, plus this one will be 3 times C3 x minus a squared. We keep on going and going like that, then C4 times x minus a cubed, and so on. So when we differentiate the power series expansion of the given function, we get this one. And then we think about f prime of a. And then again, we can easily see that all those terms will vanish except the first one. So this C1 corresponds to this one, right? The same. And the second derivative of f of x equals 2 times C2 plus 3 times 2 times C3 x minus a. So the first one will vanish, and then we have 2 times C2, and then 2 is here, and so 3 times 2, C3, 1 less power is x minus a. Plus 4 times 3 times 4 times 3, C4 x minus a squared, and so it just keeps on going and going like that. So f double prime of A equals those are vanishing, remaining one will vanish. And so this is C 2 times C2. So C2 equals f double prime of A over 2. So we proved this part is correct. This is C2. This one was C1 and this one was C0. And then f triple prime of x equals 3 times 2 times C3. And this one will vanish, plus 4 times 3 times, we just bring down 2 times C4 x minus A, and so on. And then f third derivative of f is 3 times 2 times C3, because all those will vanish. So C3 is f triple prime of A over 3 factorial, right? And so we proved that this equals C3 in the power series, which has the same format. In this original power series representation, we didn't know what C0, C1, C2, C3 are. But after we assume that this power series expansion converges, when we differentiate, we could obtain all those coefficients. So when we keep on doing and doing like that, nth derivative of f at A is Cn, and that is nth derivative of f at A over n factorial. And so of course, if you remember this formula, then you can easily say that this one is what that is. And actually, I shouldn't write down this one here. So this one is important formula you have to remember. Any questions so far? So this is the Taylor series expansion. The next one is about Maclaurin series. Maclaurin series is a special type of Taylor series when A is 0. So when we follow the same formulation, that becomes f of x equals n equals 0 to infinity. Nth derivative of f at 0, this is 0, over n factorial x to the n power. So when we expand this out, it becomes f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial x squared, and so on. So what we want to do now is we want to formulate the Maclaurin series or Taylor series when the nth derivative is known. So find the Maclaurin series or Taylor series and the radius of convergence R when the nth derivatives are given. So nth derivative of f of 0 is n plus 1 factorial for n equals 0, 1, 2, and so on. So f of x is this time this is Maclaurin series because this is 0, and we are using this formula. So x to the nth power is attached. So summation n equals 0 to infinity nth derivative of f as 0 over n factorial x to the n power. And so summation n equals 0 to infinity. So we will do substitution for this one. So n plus 1 factorial over n factorial times x to the n power. So this one will be n equals 0 to infinity n plus 1 times n minus 1 times 2 times 1 over n factorial is n times n minus 1 2 times 1 x to the n power. And so all those will cancel each other, and we have summation n equals 0 to infinity n plus 1 times x to the n power. So this is just simply using the formula when nth derivative is given. And for the radius of convergence, when we have power series or Taylor series, we use the ratio test. So we think about limit n goes to infinity, a sub n plus 1 over a n. Then that is limit n goes to infinity. So this is a n, right? So a n plus 1 will be n plus 2 times x to the n plus 1 over a n is n plus 1 times x to the n power. So that is limit n goes to infinity n plus 2 over n plus 1 times, this is absolute value of x. So this part will go to 1. And so we have absolute value of x. So by the ratio test, we must have absolute value of x is less than 1. Therefore, radius of convergence is 1. Any question? First page of the question, are you talking about this part. Okay, are you ready? Yeah. The next one is nth derivative of f at 4 equals -1 to the n power times n factorial over 2 to the n power times n plus 1. So f of x equals summation n equals 0 to infinity nth derivative of f at 4 over n factorial times x minus 4 to the n power. So that becomes summation n equals 0 to infinity. We just write the denominator as 1 over n factorial, and then we just multiply the numerator, which is -1 to the n power times n factorial over 2 to the n power times n plus 1 times x minus 4 to the n power. So this n factorial and this n factorial will cancel each other. So we have n equals 0 to infinity minus 1. Maybe it is better to combine these. Then that becomes -1 over 2 to the n power times x minus 4 to the n power, but there was n plus 1 in the denominator. So we combined these to get this part, and we combined these two to get this fraction. So again, we have to check the radius of convergence by using the ratio test. So limit n goes to infinity, absolute value of an plus 1 over an equals limit n goes to infinity, absolute value of an plus 1 times 1 over an. So limit n goes to infinity. We don't really have to care about -1 to the n power part because we are thinking about the absolute value. And so I would write down 1 over 2 to the n plus 1 power times x minus 4 to the n plus 1 power over n plus 1 plus 1. So indeed, we are talking about this part, right? Not this part. Times, we have to flip this. So 2 to the n power over 1 times n plus 1 over x minus 4 to the n power. And then we have to simplify. So that is limit n goes to infinity, 2 to the n power over 2 to the n plus 1 power, and x minus 4 to the n plus 1 over x minus 4 to the n power. We are thinking about these two, and we already did these two, and then we combine these, then we have n over n plus 1 over n plus 2. So we simplify further, then we have limit n goes to infinity, absolute value of 1 over 2 times So x minus 4, and this part will go to 1, so we don't have to write it down. So that becomes x minus 4 over 2, absolute value of x minus 4 over 2. So radius of convergence will be x minus 4 over 2 is less than 1. So we can say that x minus 4 is less than 2 by multiplying by 2 on both sides. So the radius of convergence is 2. You can, in this case, you don't really have to solve the inequality and think about the half of the interval because there is nothing in front of x. So, but if you want to solve the inequality, then you can solve like this, and we add 4 on each side. And so x ranges between 2 and 6. And so the difference is 4. And the half of that is 2. That is the radius of convergence. Any question about what I did today? So maybe I can do one more problem. The pattern of the problem is a little bit different, but I still can finish it. So find the Maclaurin series for the function f of x and find the radius of convergence r. First problem is f of x equals 9 times 1 minus x to the negative 2 power. We think about the absolute value, the Maclaurin series, and so we think about the evaluation at 0. So f of x is f to the, we didn't differentiate anything, so we can decorate with 0. Is the given function 9 times 1 minus x to the negative 2 power. So f0 derivative at 0 is 9. If you plug in 0 here, then we have 9. The first derivative of x is negative 18 times, so we multiply the digit, and minus 1 times 1 minus x to the negative 3 power because of the chain rule derivative of this one. So when we multiply digit 2, we get 18 times 1 minus x to the negative 3 power. So the first derivative at 0 equals 18. And let's do the second derivative. And that is 18 times -3 times -1 times 1 minus x to the -4 power. So if you look at this, just 18 comes from here and -3 comes from the power, and this comes from the chain rule, right? So second derivative at 0 equals 54, because these will be 54. So 54 times 1 minus x to the -4 power. So third derivative of f is 54 times -4 times -1 times 1 minus x to the -5 power. So that is minus will be plus, and so 216 times 1 minus x to the -5 power. And the third derivative at 0 is 216. And the fourth derivative at x is 216. We just keep doing the same thing. -5 times -1 times 1 minus x to the -6 power. And if you multiply all of them, and then you have 1080 1 minus x to the -6 power. So fourth derivative at 0 equals 1080, and so on. So when we expand that to Maclaurin series, that goes like f of x equals f of 0 plus f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial x squared plus f third derivative of f at 0 over 3 factorial x cubed plus fourth derivative of f at 0 over 4 factorial times x to the 4th power, and so on. So nth derivative of f is at 0 over n factorial x to the n power. So we've been getting all the values here, and then we will try to think about the pattern. F of 0 was 9, and f prime of x 0 is 18. So we will write 18 here. X plus f double prime of 0 is 54 over 2 factorial x squared plus third derivative of f at x is 216 over 3 factorial x cubed plus fourth derivative of f is 1080 over 4 factorial x to the 4th power. So if you look at this, this is 9, and this one is 18, and this one 2 factorial is 2, so that'll be 27. And then 3 factorial is 6. So when you divide that, we get 36. And well, when we think about 4 factorial, 4 factorial is 24. So when you think about the fraction, that becomes 45. So there is a pattern and the coefficient. So that is 2 times 9, and then 3 times 9, and 4 times 9, and 5 times 9. So that means 9 is a common factor, so we can pull that out. And so 9 summation n equals 0 to infinity n plus 1 x to the n power. When we formulate that, because this goes like 1, 2, 3, 4, and so on. So that's how this n plus 1 come from. And then we want to think about the radius of convergence. So we have to use the ratio test again. So limit n goes to infinity, absolute value of an plus 1 over an. And then that is limit n goes to infinity, absolute value of an plus 1 is 9 times n plus 2 times x to the n plus 1 over 9 times an is n plus 1 times x to the n power. So those two will cancel each other. So that means limit n goes to infinity. We have n plus 2 over n plus 1 times, for this part, x to the n plus 1 over x to the n power, which is x. So this part will go to 1, and this is a fixed random number. But when we think about the limit, it will be absolute value of x. So by the ratio test, we have to have absolute value of x is less than 1. So the ratio, radius of convergence equals 1. So that's it for today. And definitely I finished the exam ranges material. What I'm saying is that I have to do more to finish 11.10, but the pattern of the problem which will show up in the exam 2 will be up to the course material I covered today. Any question? If you don't have any question, then you can leave, and I will see you tomorrow.